This is the story of one of the most comprehensive programs ever undertaken between an aircraft designer and an engine manufacturer. Its objective, the testing, refinement, and certification of a propulsion system as applied to a new concept in air transport. At various plants and installations throughout the United States, millions of engineering hours were poured into a highly integrated program of research, testing, and production development. For example, at Indianapolis, the long-range development and broad pre-testing program. At Dayton, extensive propeller research and proof testing. At Marietta, Georgia, a wide-scale ground and flight testing program with the C-130 Hercules. Eglin Air Force Base in Florida, takeoff and landing operations on unimproved fields. Ardmore Air Force Base, Oklahoma, full-scale troop and cargo operational tests and engine familiarization. Cold weather tests in sub-zero temperatures at Bemidji, Minnesota, and Anchorage, Alaska. Military performance and accelerated service tests at Edwards Air Force Base, California. Long-range ground and flight tests, endurance and operational flying at Lockheed's Burbank facilities. And in San Diego, the quick engine change package developed at Rohr Aircraft. The master plan for all this test and development work was coordinated through charts similar to this one. Each group within the master chart represents a separate phase of activity managed by one of the 5 principal agents participating in the overall program. The Allison Division of General Motors, which of course was responsible for engine design and development, as well as a wide range of laboratory and flight testing. The Aero Products Corporation, who designed and developed the 606 propeller for use with the D-13 engine. Rohr Aircraft, who developed the quick engine change package for fast installation and ease of power plant maintenance. Lockheed, in addition to its full Electra design work, conducted all final testing of the total power package and shook it down in an exhaustive series of ground and flight operations. And the United States Air Force, which, with its own full-scale C-130 Hercules program, tested the basic power plant for many thousands of operational hours and made its findings available to the company as a contribution toward the Electra program. By September 1958, there will have been accumulated from all test areas a combined total of some 350,000 ground and flight hours on these engine propeller combinations under the broadest possible range of weather and operational conditions. Further, it is estimated that by the latter part of 1959, the Electra transport with this power package will itself have accumulated over 500,000 engine flight hours in actual airline operation. This, then, is the scope and meaning of the Lockheed General Motors Master Propulsion Program. It's been in full operation since 1956 and will continue to operate well past the Electra certification date.
Lockheed pioneered in the application of turboprop power. Early designs in 1953 were the military R-7V2 and the C-121F. These 2 planes were used by the Navy and Air Force in an extensive survey of turboprop propulsion. They were followed in 1954 by the full-scale production of the C-130 Hercules, the world's first transport designed specifically for the utilization of prop jet power. This propulsion system was the forerunner of the Allison D-13 commercial engine. Before this airplane was assigned to regular squadron operations, the Air Force put it through exhaustive shakedowns in the various types of service it was later to see. Landings were made on sand and clay-topped fields where the broad foot of its tandem gear responded as if it were touching down on improved runways. Debris and dust kicked up by reversing power had little effect on engine performance. From these unimproved fields, takeoffs were made repeatedly under full load, and the standard 50-foot obstacle was cleared in less than 2,200 feet. At 48 degrees below zero and equipped with ski landing gear, the airplane proved operationally suitable on snow-topped Alaskan runways, landing at 70-knot touchdown speeds and stopping in less than 1,000 feet with application of reverse propeller thrust. At Bemidji, Minnesota, other tests in sub-zero temperatures were carried out. Quick engine starts were made as a daily routine, without preheating devices, even after long periods of cold soaking in the open. Every opportunity was taken to confront the engines with rough weather. In all situations, acceleration and deceleration responses were normal. With its standard wheel landing gear, the Hercules lifted off icy runways with gross weights up to 111,000 pounds. Engine endurance checks included full range and maximum speed regimes. During extended flights, intentional engine shutdowns were observed in these fully instrumented ships by means of closed-circuit television systems. Air restarts were made consistently without incident, even with temperatures running to 48 degrees below zero. Today, the United States Air Force has the Hercules fully operational in squadron service, entrusting the delivery of troops and supplies to hundreds of these aircraft with their Allison prop jet propulsion, as the airplane fulfills its mission of global workhorse. In the commercial transport field, meanwhile, Lockheed was projecting new designs and new criteria for the inevitable shift to turbine propulsion. A careful air transportation analysis made at that time had a vital bearing on the type of equipment proposed to meet the growing needs of the world airlines. In this study, it was found that within the total world system, approximately 60% of all commercial flights fell within the category of 500 miles or under, while 80% of all world flights were seen to be less than 1,000 miles long. Thus, it became patently clear that the short and medium-length hauls did, in fact, constitute the bulk of the world's air transport business. Yet this was, historically, the portion of the system most neglected from the standpoint of airline economics and functional design. Lockheed, therefore, undertook a broad study of the special equipment needs of the short and medium hauls, with the premise that the mission should dictate total design requirements for the new air transport. A prime consideration in these studies was the selection of the right propulsion system, one which would deliver balancing factors of speed, performance reliability, and economy. After extensive investigations, the Allison D-13 prop jet engine, coupled with the Aero Products 606 propeller, or alternately the Hamilton Standard, was chosen as the best power package for the projected airplane. In 1955, the Electra design, utilizing this propulsion system, was selected over all entrants in the American Airlines search for the answer to the short to medium range problem. Further airplane specifications and refinements were added with the close cooperation of both American and Eastern Airlines, and subsequently many other world airline operators. In the power plant field, the Allison division of General Motors had long been established as a manufacturer of aircraft engines. Having powered 66 different models since 1937, Allison was the first American manufacturer to turn out a production jet engine for aircraft. In its continuing research and development program, the company operates a test center whose facilities are without parallel in the industry. With plans for future growth, the present 12 buildings and 23 engine chambers in this center alone provide for the examination of both theoretical and practical problems. In the course of early research, Allison explored the means for combining the best aspects of pure jet power with the efficiency of propeller thrust, seeking to achieve important savings in weight, fuel consumption, and altitude flexibility.
A series of developments produced the 501D13, which today powers the Electra. This highly efficient engine produces 3,750 equivalent shaft horsepower, or approximately 2.5 horsepower per pound of engine weight.
But back of this production article lies a long program of analysis, probing the performance of every component vital to the engine's operation. Blades of the compressor and the turbine, for example, were evaluated for a variety of design and material behaviors. The tests led to a reduction in vibration levels, better resistance to corrosion and heat, and expanded engine capabilities. In the altitude-attitude test cell, a wide variety of climb and dive positions and altitudes up to 60,000 feet were simulated with operating engines. The resultant fixes produced better scavenge and main pumps, improved oil feed, and more efficient lubrication of accessory drive gears. In the climatic test chamber, engines ran typical airline schedules of starts, stops, and endurance to test engine performance under extreme temperatures and humidities. To examine the effects of hail on an engine operating at full flight speeds, salvos of hailstones up to the size of baseballs were fired at speeds reaching 415 miles per hour into the inlet duct, with no operative damage to guide vanes or compressor blades. Another series fired the pellets directly into the engine. Photographed at 6,000 frames per second, these hailstones are traveling up to 425 miles an hour. After one series of 30 such firings, 2 guide vanes ultimately gave way, but the anti-ice shield and inlet temperature probe, although deformed, were not ruptured. Later tests revealed that the probe suffered only a negligible shift from its initial calibration, and a complete teardown revealed no other damage to the engine. Demonstrating ability to withstand ingestion of birds, 4-pound chicken carcasses encased in paper cylinders were fired into the inlet duct at both taxi and medium flight speeds. While the CAA does not require this test, officials nevertheless noted that the engine could ingest birds of this size without excessive structural damage and still continue operating. In Allison's Operation Hourglass, a YC-131C completed a 1,000-hour endurance test in 84 days, averaging 12 hours of flying per day. Only routine line maintenance was performed, and not a single major part was changed. After the final flight, engines and propellers were removed and components fully disassembled. Most of the parts had already seen from 1,000 to 2,000 hours service prior to the Hourglass program, but critical inspection showed them still acceptable for reinstallation in the same engines, ready for additional flight demonstrations around the country. The propellers, too, passed critical inspection and were likewise returned to service. Findings brought out in research were applied in the manufacture of production engines. By joining a chilled shaft with heated turbine wheels, a permanent bond is created. Normalizing the temperature under pressure holds tolerances within 0.02 of an inch in stack dimension. Each blade is, of course, again checked for position and clearance. Since these units rotate in flight over 13,000 RPM, the highest standards of accurate balancing are maintained. Each wheel of the turbine and the compressor were individually balanced previously, but both assemblies are again checked dynamically before final assembly into the engine. In final assembly, the turbine, compressor, accessories, and gearbox come together, and the engine is made ready for a functional checkout in an operating test cell. At the Aero Products plant, each blade is balanced horizontally and vertically against a master, a method which ensures positive interchangeability. Propeller subassemblies, with dummy blades attached, are worked hydraulically for critical examination of all mechanical operations. Dynamic balance is achieved during functional reliability tests. The spinner, too, is balanced with the same degree of precision given the propeller. With the propeller mounted, every engine gets an initial run of about 3.5 hours to break in all seals and for adjustment of engine controls. A second run is made following complete disassembly and re-examination to complete the checkout of each production engine. Meanwhile, at Lockheed's Burbank plant, a Super Constellation test vehicle was fitted with a complete Electra power package in the number 4 position. Several months in advance of the first Electra, this phase of the development program was undertaken to prove out compatibility of the Allison engine and Electra nacelle. To install the D-13 power plant, the supporting structures for the engine were redesigned. For complete evaluation of engine performance and environmental conditions, a network of pressure sensing lines, thermocouple leads, and wiring instrumentation was installed. Inside, these lines were brought through to the various data recording panels. On an average check flight, a typical crew consisted of 5 or 6 test engineers, in addition to regular flight personnel.
Turning forward.
The test spanned many months and covered all aspects of engine and propeller performance. Results were fed back continuously to both Lockheed and Allison engineering staffs. The quantities measured, in addition to normal engine parameters, included hundreds of pressures and temperatures throughout the various power plant zones. The oscillograph recorded transient quantities during various tests, including propeller vibratory stress surveys. Because this plane was not pressurized, crew members used oxygen equipment at altitudes above 10,000 feet. Brown recorders allowed continuous monitoring and recording of over 300 operating temperatures, including separate engine components, accessories, and the complete fuel and oil systems. Tests of dynamic pressure conditions existing at the face of the compressor inlet not only proved out Electra nacelle design, but showed that it achieved more than 100% ram pressure recovery at the engine inlet. Out of this program and its resultant modifications was drawn further confirmation of the engine's flight performance, as well as proof of the compatibility of the complete propulsion system in the Electra nacelle. A second super constellation was fitted with 4 complete Electra power packages, including 606 propellers. It thus became the first test vehicle to fly as a simulated 4-engine Electra. This airplane flew accelerated schedules, furnished by airline operators, during a program which spanned several months. It sought out extremes of weather and ice over short and long distance routes, while carrying out simulated schedule commitments. Other information obtained included surveys of fast turnaround capabilities, bottle engine starts, line maintenance, and data on this propeller's unique system of phase synchronization. The information gained was directly applicable to the Electra program and was made available to the CAA for certification considerations. Out of the total coordinated program, each of the specialized tests help to confirm the sound engineering concept, which is the Electra propulsion system. The findings reveal that all performance guarantees were either equaled or surpassed. As production models make their appearance in check flights, exciting new values are revealed. Inherent in the Electra's performance, for example, is the ability to deliver an instantaneous power response in wave-offs or in other demanding situations. This capability is available only with Allison constant speed prop jet power. Out of all of this accumulated experience comes the growing conviction that the Electra is truly the new standard of the industry for the short and medium airline flights.